Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello everyone, thank you for joining us today and welcome to this AI for Good session on towards vision energy with the help of AI. Many thanks to our speaker, Dr. Stephen Brunton, professor at the University of Washington, for accepting our invitation. I'm Gerharge from the International Atomic Energy Agency. The IAEA is the World Center for Cooperation in the nuclear fields and seeks to promote the peaceful uses and applications of nuclear technology. This AI for Good session will give an overview of how machine learning can contribute to scientific discoveries, especially in fluid mechanics. Please type your questions and comments into the neural network chat function. We'll try to go through those during the session. Without further ado, please welcome Dr. Stephen Brunton, who will tell us about his work in data-driven mechanics.
Thank you so much for the kind introduction and also for the invitation to be here. So it's really my pleasure to tell you about the work that we're doing at the interface of machine learning and fluid mechanics. I will point out that most of what I'm going to tell you about today applies beyond fluid mechanics to other fields of science and engineering, things like disease modeling, neuroscience, climate science. Any system that's high-dimensional, nonlinear, and multi-scale, you can use these techniques. So I also want to acknowledge my many excellent co-authors, collaborators, and partners in this work. Especially the middle row are excellent postdocs and graduate students who have done most of the work I'm going to highlight today. And if you are particularly interested in how machine learning can apply to fluid mechanics, we wrote this annual review of fluid mechanics paper a few years ago, which really zooms into this particular use case and application. But today, again, I'm going to talk more generally about scientific discovery. And so this will apply to systems beyond those just in fluid mechanics. So what I like to point out is that there is this emerging field of machine learning. It's been on the center stage scientifically for the last decade or so. But at the end of the day, machine learning can be oversimplified as simply building models from data using either optimization or regression techniques. And when we say it this way, it becomes clear that these are tools we've been using for at least the last 7 decades. Since Kalman and the Kalman filter in the 1950s, we've been building models from data using optimization and regression. And I would point out that if you think about scientific discovery, we've actually been doing this for centuries, if not millennia. So all the way back into the Roman times and even prehistory, people were building models of how the stars moved and how the weather changed from observational data. Now, the tasks that we have in engineering systems in blue are typically things like reducing the dimension of a very high-dimensional complex system, or modeling how those patterns co-evolve in time. Maybe how do I place a few sensors on a Boeing aircraft wing to estimate and control that system? All of those challenges in blue end up being very hard optimization problems. They're hard specifically because the physics is nonlinear and multi-scale in space and time, which leads to these optimization problems being very high-dimensional and very non-convex. And high-dimensional non-convex optimization problems are exactly what machine learning is getting very good at. Okay, so what I want to point out is that we actually are starting to have a good chance of solving these challenges in blue using emerging machine learning optimizations. And the reason we think that it's possible to do this for complex systems, the reason we think that we can solve these tasks in blue using machine learning, is fundamentally because patterns exist in your data. So even very, very complicated data like this fluid flow, atmospheric cloud flow past Guadalupe Island, dominant coherent structures, patterns emerge in this system. That's why we think we can apply this to fluid systems, and that's why we think that machine learning has a chance of working in the first place. These take advantage of patterns in your system. If you're interested in reading about this specifically in the context of fluid dynamics, there's this nice review paper by Sam Tyra and colleagues in this 2017 AIAA journal paper, where we talk about how to extract these patterns, how to work these patterns for fluid flow systems. Today, I'm going to talk a little bit more generally about scientific discovery, though. So not just discovering and using patterns for engineering objectives. How do I actually make scientific discoveries using machine learning? So I'm going to segue a little bit into that. And I think what I want to do here is first motivate that out of all of the possible types of machine learning solutions, many of us think about machine learning as being almost synonymous with deep learning or neural networks. And I don't think that that is a very practical perspective. Out of all of the types of machine learning that are available, I want us to be thinking particularly today about machine learning that is interpretable and generalizable, that gives models that are both interpretable and generalizable, especially if we are going to use these in safety critical systems like on an aircraft that we design, or in an automobile or a train or a nuclear reactor. The solutions, the models that we build had better be both interpretable and communicatable by humans, and they have to be able to generalize beyond the training data that we use to generate these data. Okay, good. So instead of defining these, I want to give you my favorite example, which is the Newton's second law, F equals ma. This is in many ways the ultimate interpretable and generalizable model. So it's clearly interpretable in that this model has three terms: force, mass, and acceleration. They have units. You can write them down for a particular problem of interest and analyze them and discuss them with a friend. They're interpretable. And they're generalizable in the sense that you can learn this rule from an apple falling on Earth, and it's still true when we decide to land humans on the moon. That's the ultimate generalizable model. And that's the kind of power we want our machine learning models to have, is not just to be very, very descriptive, but also to have this generalization and interpretability criterion. And this is not just Isaac Newton and the Newton's second law. This has been the gold standard in physics for 2,000 years, from Aristotle to Einstein. Models that generalize are the models that are as simple as possible, but no simpler. This is the principle of parsimony. This is Occam's razor. And this is how we have determined as humans what is physical for millennia, is that the models that are as simple as possible, but no simpler, tend to have the best chances of generalizing because they're not overfitting. And this is very much in contrast to the modern perspective on deep learning, which is to over-parameterize everything, to have millions of free parameters that you can tune. I want my models to be as simple as possible and have as few descriptive variables as are necessary to describe the phenomena at hand. And so mathematically, in the modern era, we have some tools at our disposal to promote models like this. And specifically, we want our models to be low dimensional and sparse. Low dimensional means even if my system originally had millions or billions of degrees of freedom, I want to identify the few coherent patterns that matter for my decision-making process. So, out of a million or a billion variables, I don't want to get distracted. I just want to focus on the key low-dimensional structures. And then sparsity means if I have a differential equation describing how those variables co-evolve in time, I want that differential equation to have as few terms as possible, to be as sparse as possible. So that's what I'm going to show you today, is how we build these models. And this is the picture we end up drawing in my lab quite a lot, are these deep autoencoder networks, where you essentially learn an encoding variable Z from your original high dimensional measurements X through something like a deep nonlinear autoencoder network. And those latent variables Z, those low dimensional states Z, we learn them specifically so that they admit a sparse differential equation, Z dot equals F of Z. So if we fast forward to the modern computational era, this starts to look a lot like Lorentz's 1963 model for chaotic thermal convection. So this model, written down on the right, is a differential equation that models the chaotic thermal convection observed in the Earth's atmosphere. Here's a movie of chaotic thermal convection. And you'll notice that this Lorentz 1963 model has all of the features that we want our machine learning models to have. It's low dimensional, written in terms of three variables, x, y, and z, which are the amplitudes of three spatial modes proposed by Saltzman a year earlier. So it's low dimensional. And it's sparse in the sense that out of all of the possible right-hand sides that could describe these dynamics, this differential equation has only 7 terms and 5 of them are linear. It's about as sparse as you could possibly get. In fact, it is as sparse as you can get and no sparser. So this has those 2 key features of low dimensional and sparse, and this makes this model more interpretable and generalizable. It's been an extremely successful model in the last 6 decades. So I'm going to show you how we discover models like this, and I'm actually going to warm up on the Lorentz 1963 system. So this is what we call the sparse identification of nonlinear dynamics, or SINDy algorithm. And the idea here is that if you had measurement data from the system, so you measured x, y, z, and you compute x dot, y dot, z dot, the time derivatives, maybe we don't have access to the governing equations, though, we just have data. The simplest model you could build would be a linear regression model, a DMD model, which is essentially a 3x3 linear system that maps x, y, and z into x dot, y dot, and z dot. Now, this is too simple. This model is too simple because it only has a single fixed point at the origin. It's a linear system, so it only has a fixed point at the origin. It's not rich enough to describe the behavior of this Lorentz system with multiple fixed points, multiple unsteady periodic orbits, and chaos. So instead, what we do is we augment our right-hand side to include more candidate terms that could describe these dynamics. In this case, I've added polynomials up to 5th order. You can do anything you like. You can put any terms in this library you like. These are all computable from the primitive measured variables x, y, and z. And so now the goal is to find the simplest model that describes x dot, y dot, and z dot, which means the sparsest or fewest columns of theta that add up to equal x dot, that add up to equal y dot, and that add up to equal z or z dot. And so in this process, essentially finding the fewest columns of theta that add up to x dot, y dot, and z dot, 20 years ago, this would have been an NP-hard brute force search. Now, this is a commodity set of algorithms. There are dozens of good sparse regression algorithms on the market to find this. And you'll notice that the terms that are highlighted in blue, in red, and in green are exactly the terms from the original Lorentz system that generated this data. So in this way, we are structurally learning the actual differential equation that generated the data. Now, if you're interested in trying this out, I would encourage you to check out our SINDy open source software package. Everything we do, everything I'm going to show you in this talk is completely open source. And so you can download this and try this out yourself on time series data that you have. I'll also point out that you don't just have to use this to model ordinary differential equations. You can also model partial differential equations. So this is work by Sam Rudy when he was a PhD student working with Nathan Kutz and myself about 5 years ago. And in this case, what he did was he took spatial temporal data, for example, this flow past a cylinder, and instead of building a library of regular derivatives and terms, we can now build a library of partial derivatives and products of partial derivatives. And so if I set this problem up to find the fewest columns of theta that add up to equal omega dot, or the time derivative of vorticity, then we learn in panel D that the simplest model describing the data, but no simpler, is in fact the coordinate form of the Navier-Stokes equations. This is the Navier-Stokes equations with the Reynolds number within 1% of the actual value. So this is pretty cool. Even very complicated PDEs you can learn just from measurement data. I'll point out that because the data is so vast, we can get away with massively subsampling the data. As long as you can compute partial derivatives in those patches, there's usually enough data to do this identification procedure from dramatically subsampled data. Now, the two examples I've shown you are what we call rediscovery, because we knew the Lorentz system, that's how we generated the data. We knew the Navier-Stokes equations, that's how we generated this data. But in the years since these algorithms have been introduced, they've actually been used to discover lots of new systems where we did not have the answer ahead of time. So for example, in this partial differential equation discovery, colleagues from across the world and also within our lab have used these to discover new equations for things like magnetohydrodynamics, for plasma physics, for systems in neuroscience, for systems in active matter and rheoscopic non-Newtonian fluids. And so we're actually getting real discoveries of partial differential equations that have never been written down before. Okay, so let's do a quick recap. So the goal of SINDy is to learn dynamical systems models from data. Those can either be ordinary or partial differential equations. So if my data is like this from the Lorentz system, I might learn a sparse low-dimensional differential equation. If I have spatial temporal data like flow past a cylinder, I might learn something like the Navier-Stokes equations. And now what I'm going to do is, once we have our partial differential equation, I'm going to take a little bit of an aside here, and I'm going to show you what are some of the powerful things we can do once we have a partial differential equation for our system, either from a textbook or from this model discovery procedure. There are some pretty powerful things we can do with that equation. So I'm going to tell you about this work by Jared Callahan, who was a PhD student with me a couple of years ago, where he essentially automated one of the most successful procedures in all of applied math, the so-called dominant balance procedure. So this is a turbulent boundary layer here from the Johns Hopkins Open Dataset. You can download this yourself and try it out. And the idea here is that very, very complicated systems like turbulent fluid flows, we have been wanting to understand these systems before we could simulate them in full three-dimensional accuracy. And so what we used to have to do is you would have to make an argument that in certain regions of this boundary layer, some terms of the Navier-Stokes equations are large and in a dominant balance with each other, and other terms are small and approximately negligible. And that's what this dominant balance approximation means, is dominant balance between a few terms where all the other terms are approximately zero. This is how we've done asymptotic analysis and how we studied most of these complex systems before modern high-performance computing. So what we're going to do, just like we automated Lorentz 1963, here we're going to try to automate this dominant balance procedure with machine learning. So we're actually going to work with this data set. The first thing we're going to do is we're going to take a Reynolds averaged approach. So that means what we are going to do is we're going to take a mid-plane of this three-dimensional flow, and we're going to average in time to get a simplified Reynolds average Navier-Stokes equation, this partial differential equation you see here. This has 6 terms. It's much, much simpler than the full unsteady Navier-Stokes in 3 dimensions, but it's still quite complicated. It's a partial differential equation with 6 terms, and there are still open problems about these RANS equations. Now, what Jared realized is that you can compute each of these terms everywhere in space. So this is the plot in space of the U bar X term. That means that's the time averaged mean convection term. And you can do that for all 6 terms in the equation. And right off the bat, you can see that there are regions like this region here, where 2 of the terms are large and in balance with each other, where most of the other terms are approximately equal to 0. So this is a visual confirmation of this dominant balance idea. Next, what we can do is we can pick a single point in space. And for that single spatial point, there are these 6 numbers that define those 6 terms for that point in space. And so for every point in space, I can scatter plot this in a 6-dimensional equation space where the coordinate axes are each of these terms of the equation. So that's what we have here. These are 2-dimensional slices of a 6-dimensional equation space where we are trying to analyze the system. And you'll notice that, again, there are these subspaces where 2 of the terms are large and active and the other terms are approximately 0. So again, this seems to be highlighting this dominant balance idea. So the first thing that Jared did was he decided to cluster these points using something simple like a Gaussian mixture model. So now we have clusters. And now for each cluster, like the red cluster, we're going to try to find the sparsest subspace possible that captures most of the variance. What this means is we want the subspace in these 6 equation dimensions, that we want the set of non-zero coordinates that captures the most variance in the system. So in the case of the red, we want the non-zero coordinates to be this diffusion term and this Reynolds stress term, and all of the other subspaces are going to be 0. And so you essentially find that in the red cluster, you only need these 2 terms of the equation, these 2 coordinates to describe most of the variance. The blue and the green require a different 2 terms, and so on and so forth. The last step here, because this is each of these points corresponded to a point in space, you can replot them spatially in the boundary layer here. And in doing so, we relearn essentially that there are these regions of different dominant balance physics. So in this red region here, the viscous sublayer, only these 2 terms in the partial differential equation are large and active and balancing each other, and all of the other terms are approximately 0. Similarly, in the blue inertial sublayer, a different 2 terms are in a dominant balance with each other. And so this is pretty profound. This tells me that I only need a subset of the physics in these different regions. So this can simplify the computations and the analysis. It also suggests, you'll notice that as I go from the red into the blue, they have 1 term in common and 1 term that's different. And what that means is that there's very likely a non-dimensional number that mediates this red term turning off and this blue term turning on as I cross from the viscous to inertial sublayer. So this also suggests things like non-dimensional numbers that mediate these transitions. Okay, good. So we've applied this to the boundary layer, but we've also applied this to many other systems, including a supercontinuum high energy laser, fluid flow in the Gulf of Mexico, and also systems in neuroscience, this bursting neuron, and we're continuing to apply this to systems on spatial brainwaves in the brain. Good. And so this is one of the ones I'm most excited about because you can try this yourself. So for example, if you have spatial temporal data and you believe it's governed by a partial differential equation, you can compute these data-driven clusterings yourself and cluster your data based on which subsets of the physics are active where. Okay, so remember how I said that this also suggests non-dimensional numbers? That got us thinking that we could probably generalize the Buckingham Pi theorem also using machine learning. So this is work by Joe Bakerjee, who is a postdoc working with Nathan Kutz and myself. Joe is brilliant and he's on the job market this year. So if you have openings, I strongly encourage you to consider him. So the idea here is that if you have a physical system, this is a toy system on the left of a bead or a mass on a rotating circle, a hoop. And this has 5-dimensional parameters, the mass, the radius, the dissipation, gravity, and the frequency. But we know that in this system, there are 2 non-dimensional numbers that dictate all of the behavior of the system. And so what we have done essentially is develop a non-dimensional system where we can learn dimensionless parameters that dictate these systems from data of the dimensional system. The way we do this essentially is you'll notice that if you took these 2 parameters and took their logarithm, you would have log of r plus 2 log omega minus log of g. Each of those log terms have integer coefficients. So +1, +2, -1, based on where they are in this fraction. And so if you log your dimensional data, now again, we are trying to find a sparse combination in the null space of those logged parameters. And in doing so, you can learn these dimensionless groups that correspond to these known solutions. So you can also apply this to the fluid flow I showed you earlier. So essentially, this is that boundary layer I just showed you. This is the known self-similarity scaling, the Blasius scaling. This is what pops out of our non-dimensional Buckingham Pi network. And you'll notice that these exponents are not perfectly 1/2, but they're close enough that a human could then go in and polish these with expert knowledge. Okay, so we can now learn these regions of dominant balance physics, and we can also learn non-dimensional numbers that dictate the transition between these regions. Okay, so that was kind of this zoom in to what you have if you have a partial differential equation. So we can learn ODEs and PDEs. There is a third option here, which is if I have a spatial temporal system like this flow past a cylinder, I could decompose it into a set of orthogonal modes, these three orthogonal modes here, and then try to model the amplitudes of those modes as an ordinary differential equation. So this is actually a lot like what Lorentz did in 1963. He was modeling a spatial temporal system, but he projected that system onto three orthogonal modes proposed by Saltzman. And so this is the third path in the SINDy architecture, and this is what we call coarse graining or reduced order modeling, is where we take a partial differential equation system and we reduce ourselves to a specific configuration like this flow past a cylinder where we have an orthogonal basis to project onto. So we've known that we can do this for decades. For example, in 2003, Bernd Nowak showed us that if we measure this flow system in these three orthogonal modes on the left, given by the proper orthogonal decomposition and this so-called shift mode, that we can write our system as this differential equation, and this captures a lot of the phenomena of this flow past a cylinder. So we thought it would be interesting to try out our SINDy approach on this example, where we essentially measure the system in these X, Y, and Z coordinates, and we use our library regression procedure. So in doing so, we learned that the structure of the nonlinear model that's most consistent with this data is, in fact, the Bernd Nowak model here. And our identified system reconstructs almost perfectly the true behavior of the full system, including this slow parabolic manifold. So this is very promising and reassuring that, again, we can rediscover a model that is very prominent in the literature and has been the successful model for the last 2 decades. So after writing this down, I was contacted by Jean-Christophe Loiseau from Paris Tech, who essentially showed me that you can improve this dramatically with 2 very simple innovations. The first one is because we know so much about the fluid system. In fact, we know that it conserves energy because of skew symmetric quadratic constraints on the nonlinear terms. We can enforce those skew symmetric constraints in our models. When we do our SINDy regression, our sparse regression here, we can add a linear constraint on those equations. This is essentially one more line of code, and we can enforce that stability by construction. So that's a huge benefit. That might be my favorite new innovation in SINDy, is that you can enforce symmetries and constraints directly in the equations. The second key innovation over here is that instead of limiting ourselves to quadratic dynamics, so we tried quadratic because Bernd Nowak's model was quadratic, you can allow yourself to have higher order nonlinear terms, cubic, quintic, septic, third, fifth, seventh order terms, which essentially account for the dynamic effect of low energy modes that we have truncated. Okay, so there are modes that we have truncated. We're only modeling the first mode pair, X and Y, mode 1 and mode 2. This captures 96% of the energy, but these modes are dynamically important, and they can arise as their effect comes in as these higher order terms in the X and Y dot dynamics. And so by adding those terms, we essentially get a closure model, a rudimentary closure model for this laminar system. So let's see how it performs. The idea here is that in this cavity and cylinder flow, these are our benchmark systems. In the right column here, we have essentially this A delta, that's our shift mode. That is a proxy for the drag coefficient. It's something we care about as engineers. And the white curve is the ground truth from high fidelity simulations of that shift mode evolving in time. The yellow and blue curves are the industry best standard Galerkin projection onto POD modes with 3 or 7 modes. So this is kind of the previous state of the art. You'll notice that they are quantitatively not very accurate. They have the wrong rise time, they have overshoot, and they have significant steady state error. These are all big issues in these models. But when we try our SINDy models, and our SINDy models either with the cubic constraint or unconstrained, but with either with the symmetry constraint or unconstrained with cubic terms, we almost perfectly capture numerically these responses. So this is a much more accurate model when we do SINDy. But it's not just accuracy that matters. The fact is that these are also very sparse models. These are much simpler models. And so because they're sparse, you can write them down on a piece of paper and manipulate them. And this is what JC got when he actually wrote these down and played around with them. He found that this is the model for the cylinder flow. The almost perfect numerical accuracy of this model on the lower right is given by this very interpretable equation that essentially says that this flow behaves like a spring mass damper with a nonlinear damping coefficient. It's about as simple of a system as you can get, but no simpler. So that's what I really like about this, is the interpretability of these models. So next we started applying this to higher complexity flows. In this case, we have the fluid flow past 3 cylinders, the fluidic pinball system. And here we pretend that we don't have access to the fluid flow wake. We only can measure the forces, the lift and drag forces on these 3 cylinders. So here you see lift, the different lift forces versus each other for this. And essentially, with our low-order SINDy model, we can build, even just with lift and drag measurements, a very simple differential equation that almost perfectly matches the high-fidelity numerical simulations in yellow. So this solves a lot of problems that we have in classical modeling. We can now model just in terms of these intrinsic lift and drag coordinates. And since we started with these initial problems, we have scaled this up to a lot more complex systems. Things like this fusion reactor in the lower left. This is a full 3-dimensional simulation of a fusion reactor that we got working with SINDy. In the upper right, we have chaotic electroconvection, which is like Rayleigh-Benard convection, like the Lorentz 1963 problem, but with more symmetries and constraints. And we've also applied this to a fully turbulent set of experiments, both by Richard Zeeman at TU Braunschweig and by George Regas at Imperial College London. In all of these cases, we were able to learn low-dimensional differential equations x dot equals f of x in terms of a low-dimensional state x and a sparse differential equation f. So these are interpretable and generalizable models. Okay, good. Since I have a little more time, I'll tell you a few of the other things we've done since introducing these methods. So you can essentially think of all of the fluid flows I showed you on the previous slide, on this slide here. All of the low dimensional states X came from the proper orthogonal decomposition, which is essentially what we call principal components analysis or singular value decomposition in fluid mechanics. And the idea is that you take your system and you try to find a best fit linear subspace in this high dimensional space that captures most of the variance of your system. So in this case, with 6 POD modes, 6 orthogonal modes, I could capture 99.9% of the energy in my system. And if you like, you could think of this as a solution of a shallow linear autoencoder neural network. Now, I highly recommend that you don't use a neural network to compute the POD. It's the worst way you could possibly compute this. But the reason I'm showing you this is because if you think about this dimensionality reduction as a solution to a linear neural network, you can relax the linear shallow assumptions and have a nonlinear deep autoencoder and get better compression and essentially describe your data with less coordinates. So instead of modeling your data with a subspace, we are now modeling our data with a submanifold, and we can get away with many fewer variables when we use these autoencoders. So this is the picture. We have a very high dimensional system X. We're trying to learn a low dimensional set of coordinates Z that parameterize the submanifold on which that data lives. And specifically, we want to learn a Z that admits a sparse differential equation Z dot equals F of Z. So when we think about this, the reason I think that the coordinates matter so much is, again, rooted in the history of science. So if you look up at the night sky, we're in the blue dot. This is what we see when we look up at the night sky. This is what all humans have seen for countless millennia. It's pretty complicated. The planets in red make really strange paths. They make retrograde motions. Sometimes they turn around. And it's very hard to learn Newton's second law, F equals ma, in this coordinate system. But if we fix our coordinate system and we put the sun at the center, now everything becomes simple ellipses, and it's much, much easier to learn Newton's law, F equals ma, in this correct coordinate system. So that's the idea, is that we sometimes need to learn the right coordinates z so that we can learn a good low-dimensional differential equation z dot equals f of z. And that's exactly what Kathleen Champion did in her PhD thesis work a couple of years ago, was combine this autoencoder neural network with the SINDy sparse nonlinear modeling procedure to simultaneously learn a good coordinate system z that admits low-dimensional sparse dynamics z dot equals f of z. Now, this is a pretty complicated optimization procedure because the coordinates and the dynamics are stiffly coupled together. And so the loss function is fairly complicated to make sure that these are trained together, that you simultaneously are learning the coordinates and the differential equation. This is probably my favorite recent innovation in SINDy, because this allows you to simultaneously solve for coordinates and for differential equations, which again, in the history of science, almost all of our major discoveries of equations were preceded by a discovery of coordinates. Okay, good. So I'll give you a couple more examples and then I'll stop for some questions. So let's see how this works on a really complicated fluid flow. So this is flow past a cavity, but at higher Reynolds number than before. And essentially what we can do is we can build this large, deep autoencoder network like Kathleen suggested, but we can use knowledge of the physics in this decoder network. Essentially, we can build the decoder network using knowledge of the physics that we have these triadic interactions. Because my Navier-Stokes equations for fluid flow have a quadratic nonlinearity, I know how frequencies add and kind of resonate with each other through the physics. And so I can build this decoder network for free. And this is work by Jared Callahan and Jean-Christophe Loiseau. And in this system, essentially, because it's a very complicated, almost turbulent fluid flow, there's actually a large number of modes that you would need to describe the system. So instead of just 2 or 3 modes like the Lorentz system and all the other systems I showed you, this one needs 20 or 30 modes, which is very hard for SINDy to build a model out of. So what JC came up with was essentially a nonlinear correlation analysis that allows you to pick out of all of these modes which are the ones that drive, kind of dynamically drive all of the other modes. And in identifying these, you find that the blue and the red modes are the ones that are dynamically relevant. And all of the other modes are kind of algebraically pinned to those driving modes. And when you apply SINDy to these modes, you essentially find a very simple model that we get a Stewart-Landau, a coupled system of 2 Stewart-Landau oscillators with weak epsilon coupling between these modes. And in doing so, we are able to almost perfectly capture the harmonic response. This is the power spectral density of the system. We capture all of the resonant peaks and the spreading and mode mixing, which is almost impossible to capture with traditional reduced order modeling techniques. So another way you can approach these turbulent systems, this is again work by Jared Callahan. Another way you can approach these turbulent systems is by modeling the stochastic differential equation, essentially this Langevin equation on the left for the drift diffusion dynamics of your complicated system. So the goal here is that if you have a turbulent system, you can model the dynamics of the coherent structures in X, and then all of the truncated scales, all of the multi-scale structures that you're neglecting, enter in as correlated noise. So I'm not going to dwell too long on this slide, but the idea is that you parameterize both the drift and the diffusion dynamics as you would in SINDy. And now you're trying to learn the parsimonious model for these dynamics that best describes the observed phenomena. And in all of the cases we've looked at, from very simple toy problems all the way up to fully turbulent wake dynamics in actual experiments, you learn very interpretable, simple differential equation models that have both the coherent structures and the effective truncated multi-scale dynamics. Okay, so this is a pretty good place for me to kind of pull back and summarize and maybe try to just give you a brief summary so that we can answer, have some question and answer period. So maybe what I'll do here is I will just go back to this summary slide. The goal of SINDy is to learn dynamical systems models from data. And this can have the form of either ordinary or partial differential equations. We can do things like add constraints. We can discover these coordinates using autoencoder networks. Kind of the sky's the limit in how you decide to parameterize these models. But in all of these cases, the goal is a low-dimensional and sparse differential equation, because that gives us the best hope of having models that generalize and that are interpretable. Okay, so I'm going to conclude here. Thank you so much for your attention, and I'd be happy to answer any questions.
Thank you very much. There are a few questions for you. So someone is asking regarding SINDy if the user has to predefine the feeders for fitting, or if it supports auto-regression machine learning approach as well.
So generally speaking, we do think of the SINDy procedure as you essentially choose a library in which to represent your dynamics. So usually the user will choose this library theta, but this is not necessary. This doesn't have to be, the user doesn't have to specify these dynamics, the library. So you could try different libraries and see which one works better. If you know something about the physics, you could let that guide your choice. Or there are ways that you might be able to use genetic programming to kind of evolve these libraries simultaneously with the learning process.
Great,
Good
thank
question.
you. Someone is also asking regarding responsibility. Who is liable if an AI makes a costly error?
Yeah, so that's a great question. I think if you are using AI or machine learning and deploying this in a real physical system, you should absolutely be thinking about, how will this be used in the real world? What happens if your model breaks or fails? How do you certify your model? How do you check that your model is still accurate? These are all questions that we have already been answering in the field of reduced order modeling for decades. So we've been using reduced order modeling in safety critical systems like aerospace structures, for 50 years. And those models are imperfect. They might fail. They might not always work. And so we've already been answering a lot of these questions. There's the field of uncertainty quantification and certification. And so I would say, you need to bring those same ideas in when you're using machine learning systems. Yep.
Great, thank you. We still have a couple of minutes if anyone wants to add some questions in the neural network chat function, please do so.
Okay, well, if there's no other questions, thank you all so much for your attention. I really appreciate it.
Thank you for coming, and thank you everyone who joined us.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.